No.
Yes, ma'am.
Okay, okay. Okay, fine. Okay. Fine. So in the last class, we had started with magnetic flux. We were doing certain questions on it. One question, two questions we did yesterday. One was left from this topic. This is the last question that has to be dealt from this topic. Do one thing, note down this question quickly. Then I'll discuss the solution for it. At least first part I'll discuss. Second part, you should be able to tell it by yourself. Note it down. A coil of cross-sectional area A from here to here. Then I'll discuss it. And if the screen stops sharing in between, no, please just text me in the chat column. Written the question? All right. See, this question says that a coil of cross-sectional area A lies in a uniform magnetic field B with its plane perpendicular to the field. Fine. Now see, in this position, normal to the coil makes an angle 0° with the field. Normal to the coil. What do we require in our angle? Whenever we consider the angle, we require this only. in the position normal, that is the area vector which we consider. So normal to the coil makes an angle 0 degree with the field. Coil rotates at a uniform rate to complete one rotation in time t. You have to find out the average induced EMF in the coil during the interval when coil rotates. So first is from 0 degree to 90 degree position. See how we have to solve this. If one complete rotation is t, see, you people have to just analyze what is the time period that is required. Coil of cross-sectional area A lies in uniform magnetic field B, which is perpendicular to the plane. Fine. Now see, when we are saying complete time duration is t, complete time duration is t. So let's say this is 0 degree, this is 90 degree. So if complete time duration is t, we are just talking about 0 to 90 degree. It means this is this part. So 0 to 90 degree. If total was t, this is just t by 4. That's it, what you have to remember. If it is 0 degree to 180 degree, that would become half t by 2. If it is 0 degree to 270 degree, it would be t by 3. If it would be back to 0 degree, that means complete 360 degrees. So again, you will have this. This is exactly at 360 degree. Suppose the question says 180 degree to 270 degree. Your time will be again t by 4. If it is from, let's say 90 to 360. So 1, 2, 3. That is 3 by 4. In the first part, what it's saying, 0 to 90. So 0 to 90 degree means t by 4. Now, what will be your phi initial? This is BA cos theta. So this is BA cos 0 degree, which is BA. No, cross-sectional area is not rotating. Cross-sectional area, you can consider it A as it is. Second is BA cos 90 degree. So that is 0. So what is now EMF? Induced EMF. It's minus del phi over dt. So minus change in phi. Change in phi is final, that is 0. What is the change in phi? That is final minus initial, that is 0 minus BA. So this is equal to minus BA as it is. And what is the time? Time period will be t by 4. So final answer becomes 4BA divided by t, because this is minus BA. Clear? Now see, second part is saying from 90 degree to 180 degree. When we are talking about from 90 degree to 180 degree, see, you just have to understand how to pick up the time period. Rest of the part was not difficult. You could also analyze this. Yes, the rest were just questions. See, this is 0 degree, this is 90 degree, this is 180 degree, this is 270 degree, this is 360 degree. Suppose if I give you from 270 degree to 360 degree, so it would be from this, that is t by 4. Complete is t. I have divided t into 4 parts. So one part will be t by 4. If it is, let's say this is, instead of this, this is from 90 degree to 270 degree. So what will it be? 90 degree to 270 degree. That is half of total time. That is t by 2. But now in this part, it is saying 90 degree to 180 degree, that is this portion of time. So again, the time period is t by 4 itself. So this is the second part. What is the initial? It would be BA cos 90 degree, that is 0. Second part would be BA cos 180, that is minus BA. So when we'll take the change in phi, that is second phi minus initial phi. This will be 0 minus, this is minus BA. So this becomes BA. Now coming to back our EMF, induced EMF. So minus del phi over del T. This is minus, this is BA. Time period is still T by 4, so that becomes 4. This time, this is 4 BA by T. Right? Minus PA minus 0. Okay, wait. Here final is minus BA, no? See, this is minus BA minus 0. So this is still minus BA. So this becomes minus of minus BA. We are getting the same answer. 4BA by T as the previous. But answers could be different depending upon the time period that is given. So whichever time period is given, you will be able to do it, I hope. If it is 180 to 270, so just this part, that is T by 4. If 90 to 270, so T by 2. If 0 to 270, T by 3. If 0 to 360, complete T. If 0 to 90, T by 2, T by 4. If 0 to 180, T by 2. Like this, you should be able to analyze. Is this clear how to choose the time period? Because in this, the main portion to understand is time period only. Rest of this part you will be able to do it on yourselves. First, tell me, is it clear?
Sure.
Shahid, Shavez, Fia, Faiza, clear?
Yes, ma'am, clear.
All right. So you people, some of you didn't write the question, no, that time. Quickly write it down, those who haven't written the question. Then write its solution. Now we'll start a different topic. See class, coming to Lenz law. Now, remember yesterday only I have told you that minus sign I am not explaining. Why? Because we have a separate law for that. That is Lenz law. So, just wanted to discuss Lenz law with you. Lenz law, basically why we are putting a negative sign is that this is your Lenz law. It says that direction of induced current is such that it opposes the cause that produces it. That is change in flux. Now see what is meant by this. This is just the line. See, direction of induced current. Suppose this is a loop. There is a direction of induced current. It can be clockwise, it can be anti-clockwise, there can be any direction. Now, how to determine this direction? Right, how to determine this direction? So this is determined. It will oppose the cause that it producing it. See, yesterday what did we discussed? We discussed that whenever there is a change in electric flux, that is either flux is increasing or flux is decreasing, then only because of the change in flux, either it is going from increasing to decreasing or decreasing to increasing or whatever, or it's just increasing or it's just decreasing. So because of this, there will be an induced current. So if the flux is increasing, induced current will such its direction in such a manner that its aim will now become to decrease the flux. If flux is decreasing, and suppose this is the direction of induced current, so this direction will be set up in such a manner that its aim will be to increase the flux. It just has to oppose it, do the opposite work. So direction of induced current is such that it opposes the cause that produces it, that is change in flux. So Lenz law is in accordance with conservation of energy. Forget this. First, just understand what is the basic meaning of the Lenz law, because you have to do the analysis by yourself. Questions will be just given to you directly. Now see, let's do this with the help of example. Suppose let's take a coil. Let's take a coil. This is a coil, fine. Now a bar magnet, north here, south here, is being moved towards it with some velocity v, whatever. Now see, what is the approaching pole? What is the cause? Induced current will be produced. What is the cause of this induced current that will be produced? Cause is approaching north pole. Approaching north pole. Now, what is the aim? What did I tell you? It will oppose its cause. That is, repel the north pole. Repel the north pole. Yes. Bar magnet is coming towards the loop. It is coming towards the coil. So what is the cause? Cause of induced current will be approaching north pole. So what will be the aim? Aim is to oppose the cause. Do exactly opposite was the what is the cause producing it. So what's the cause? Cause is approaching north pole. So aim will be repel this north pole. If north pole is over here, this side is directed as north pole. See. So class, tell me which polarity should be developed over here so that it opposes north pole, north or south? Yes, very good. North pole. North pole will oppose it. When we were discussing dipole moment, I told you if north polarity is mentioned, that means which direction? Anti-clockwise. So now what is the direction of induced current? It is anti-clockwise. So did you get it? How did we discuss it? Approaching north pole was the cause. So this is Lenz law, that it will oppose the cause that it is producing it, that is producing itself. So if north pole is approaching, it will develop the direction. So see, now relate the law. Direction of induced current. This direction of induced current is in such a manner that it opposes the cause that produces it. And what is the cause? Cause is the changing magnetic flux. Right? So this is the Lenz law, what was written over here. Direction of induced current. We are talking about the direction of induced current. This is such that it opposes the cause that produces it. That is change in flux. See, let's take some more examples. Let's take the coil once again. This time, let's say south pole is being approached. So what is the cause right now? Cause is approaching south polarity. Approaching south pole. So aim is to repel south pole. Why? Because if it is coming towards this, see class, understand this reason very well. Why is it repelling it only? It could attract also. Why is it repelling only? Reason is that when it will come nearer, what will happen? Magnetic flux will increase. So this will develop south polarity. So what will happen? When it will develop south polarity, bar magnet will move away. So magnetic flux will decrease. And what was the aim? If magnetic flux was increasing, the aim was to decrease the flux. So aim was fulfilled. So now what's the direction of induced current? Direction of induced current, this direction is clockwise. See, look here in this question. When the North Pole, this bar magnet was coming towards this. So what happened? When the bar magnet was coming, flux was increasing. Now the aim, repel the North Pole means decrease the flux. This was the aim. So how could it be decreased? By moving the magnet away. When the magnet will move away, then only flux will decrease. So the only way to move the magnet away was by developing north polarity. Take one more example. This is the coil. This is North Pole, this is South Pole. Now South Pole is moving away. So what is the cause? Moving North Pole means flux is decreasing. What is the cause? Cause is decreasing flux, because if magnet moves away, then number of field lines will decrease. So flux will decrease. Now when the flux decreases, what is our aim? To increase the flux. This is our aim. Yes. So if we want to increase the flux, we want to move magnet towards ourselves, towards the loop. Then only it will increase the flux. If it will move further away, then it will again decrease the flux. So what we want to increase the flux right now. So how can you increase the flux? Now if we repel this, if this is repelled, this will move further away. What we want to attract North Pole this time. Clear? Why not repel? Because if it will be repelled, then it will move further away and field lines will decrease further. That's not our aim. Our aim is to oppose it. Do exactly whatever is the instruction, do exactly opposite to it. If flux is decreasing, we have to increase the flux. Yes. So if flux is decreasing and this develops south polarity, the bar magnet will move towards itself. Flux will then increase. And so what will be the direction of induced current? Induced current's direction will be clockwise. This is how you have to solve all the questions of Lenz law. One last example. South polarity is moving away. So what is the cause? If this is moving away, that is flux is decreasing. So what will be the aim? To increase the flux. How can you increase the flux? How can you bring the magnet closer? By developing north polarity. So what will be the direction? This is anti-clockwise. This I'll discuss it later, this part. So now see, direction of induced current is such that it opposes the cause that produces it. And what is the cause? Cause is change in flux. This is the Lenz law. This exactly is the Lenz law. Fine. Note it down. Then one more example I'll discuss with you. But first note down these loops examples. Done till here? See, just one more example I wanted to discuss in Lenz law. Then you people can note this down. See, this is actually, this is somewhat given in your example of NCRT, but we are doing it as a separate topic because any type of question can come from this. See, first case is that or let's take this example. This is a loop, a rectangular or a square loop. This is moving out. Fine, this is moving away. Now you have to determine the direction of induced current. So see, if this is moving out, see, field lines are here. So if this is moving out, what is happening? Flux is decreasing. Why? Because magnetic field lines are decreasing. Yes. So what will induced current try to do? Induced current will try to increase the flux. It will try to increase flux. Yes, this is the aim. Very good. This is the aim. It has to increase the flux. Now, direction of induced magnetic field I want to discuss with you. Current you will be able to tell. You will be able to mention what is the direction of induced magnetic field. See, if the aim is to increase the flux, for increasing the flux, you have to increase the magnetic field. Just tell me, class, one thing. If two, yes, Shaved, I'm repeating. See, this is a loop. This is moving outwards. Fine, this is a loop. This is moving away. Earlier, this was within this, so many field lines were included within the loop. Now, when this loop is moving away, what will happen? Flux will decrease, magnetic field, because magnetic field lines are decreased, so flux will also decrease. If something is present within here, lots of magnetic field lines are present, lots of magnetic flux is produced. When the this is moving away from it, magnetic field is also decreasing, and hence the flux will also decrease, right? So what will be the aim of induced currents, a current according to Lenz law? Magnetic field will increase, and so the magnetic flux will increase. This is the aim. That's what we have studied according to Lenz law. It opposes the cause that produces it, right? So this is the case. B increases, flux increases. Now, when this is moving away, direction of induced magnetic field I want to talk about. See, this is the original magnetic field. These yellow lines, no, which are made, these are actual magnetic fields which are present. Class, tell me one thing. If two vectors are in opposite direction, resultant will decrease, right? If two vectors are in opposite direction, resultant will decrease. Why? Because you will be subtracting the two vectors. If two vectors are in the same direction, whether this or this, resultant will increase. Why? Because you will add these two vectors, you will add these two vectors. So if I want to increase the magnetic field, this is my aim. No, if I want to increase the magnetic field, direction of induced magnetic field should be in this direction only, along the direction of the original magnetic field. See, where is the original magnetic field? Original magnetic field is pointing inwards. If I take the direction of induced magnetic field as outwards, that will decrease magnetic field because we'll be subtracting them. So this is not valid. This is incorrect. If original magnetic field is going inside the page, what you can see from these crosses, this means this is inwards, right? So what should be the direction of induced magnetic field so that resultant increases, because that is what we want according to Lenz law. That is what induced current wants according to Lenz law. So direction of induced current has to be in the same direction. Direction of induced magnetic field has to be in the same direction as that of original one. Then only the resultant will increase. Then only we can say induced plus original, this is increasing. What will happen because of this? Magnetic field will increase. Now class, remember magnetics chapter 4th we discussed. What is the direction of induced magnetic field? Inwards. So take your right hand, keep the thumb inwards. What is the curvature of fingers? If we are keeping the thumb inwards towards the screen, the fingers are going clockwise. So this becomes the direction of induced current. That is clockwise. So direction of induced current is in such a manner to increase magnetic field. Hence, this will be clockwise. So according to Lenz law, we have solved this question. Take one more example. Let's take one more example. Suppose this is the loop. This is coming into it. This is coming inwards. So now what is happening? Now the field lines are increasing. Flux is increasing. So aim will be to decrease the flux, decrease the field line. How can you decrease it? If original magnetic field is inwards, make the induced magnetic field outwards. Then only there will be a difference. Resultant will decrease. So keep your thumb outwards. See the direction of current. The fingers are going anti-clockwise. That's how you have to solve. So induced current will try to decrease flux. Magnetic field induced will point outwards. Direction of induced current is anti-clockwise in the second part. Second part means this. And first is this. This is the first part. Fine. Note it down. All of you have completed? See, motional EMF, the concept is very easy. It's just that you have to remember a very small derivation. So derivation is small, but it comes a lot in the question. So let's just discuss it. Motional EMF is what? See, motional EMF is just when EMF is occurring in motions, exactly what its name is. EMF, you already know. So this EMF is the induced EMF. And when the conductor is in motion. So now the EMF that is generated is called motional EMF. You will see how. See. Let's take rectangular conductors I've taken. Now see, towards its end, I have this is the conductor. This is just a rectangular strip that I have used. This is actually the conductor. Length of the conductor is L. All right. Now this is a movable conductor. I can move it. Let's say this is P, this point is Q. So I can slide it over this. These are just tracks. These are just conducting tracks that have been laid up. This is the magnetic field. L is the length of conductor. And let's say this is moving with V velocity inwards. Fine. This is moving with V velocity inwards. Now see, when we talk about the magnetic flux, what is magnetic flux?
Ma'am, what is that green one?
Yes.
What is that green one?
What is this?
No, I'm green.
This one, these are just simple tracks that have been laid up. These are with a certain metal or any alloy. These are just laid up so that our conductor can move on it for the experimental purposes. All right, in actual, when you will see numericals also, no such tracks are laid up. Why this is required? Because for our derivation, we require a closed area. So this is the only way with which we could. Conductor is PQ. This is just a loop that has been made with wires. When we talk about the flux, flux is BA. Now talking about the area, see, length is L. Let's say whatever area that has been left within the conductor, within this space, that is X. X is the length of loop inside the magnetic field. Length of loop inside this magnetic field. So what will be area? Area will be length into breadth. That is L into X. So this becomes B L X, right? So what will be EMF equal to? EMF will be equal to minus d phi over dt. So minus, what is d phi? This is d B L X over dt. Very simple derivation. B is constant. Forget this negative sign right now because this is because of Lenz law. Forget it right now. Length of conductor is also constant. We have dx over dt. What is dx over dt? Velocity. Yes. Yes, Fia.
Instead of BA, if I consider BS, it is same right now.
You are inaudible, Fia. Your voice is coming very low. Either just please increase your volume or just text me in the chat column. Your voice is coming very low. So this is velocity. So what is the formula? Final formula that has been achieved. The formula that has been achieved, EMF is equal to BLV. This is the formula of motional EMF. Now, why this? What happened to this negative sign? See, velocity is actually minus dx over dt. Why didn't we consider? Because velocity is in the direction where EMF decreases. Let me mention this. Velocity is in the direction where EMF decreases. That's why this negative sign has been included within it. And when we talk about this, E is equal to BLV. BA, you can use BS, any symbol you can take. FIA, you can take BA, BS, BP, BL, anything. It's just that for area, for standardization purpose, we use A as area, and for surface area, we mention S. So area, surface area, both are same. Any variable you can use. It's just that you have to take the dimensions of area itself. It's not necessary, because some books you will find BA is written BA cos theta. Some teachers teach BS cos theta. I use both anywhere. Sometimes I even do not remember with which I have started. Did I discuss BA cos theta with you or BS cos theta with you? Because it actually doesn't matter. Ultimately, you require area. Area, that is the surface area. So use AS, any alphabet, it has to be area. E is equal to BLV. This is the formula. So what is E? This is your motional EMF. This is the motional EMF. What is B? B is the magnetic field. L is the length of conductor, and V is the velocity of conductor, the conductor PQ which was sliding. That's it. This is just the derivation. Actually, it's just a one-liner derivation. That's it. This is it. But this comes a lot in many papers. I have found this motional derivation of motional EMF coming. Note it down.
I gotta scroll up.
All those who have completed till here, you people can leave. No assessment for today as well. Next weekend, we'll complete this lesson and we'll start with alternating current. Thank you so much, class.